Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The chemistry required for life beyond Earth. Life at its most fundamental level is chemistry. Every thought you think, every breath you take, every movement you make results from chemical reactions occurring in your cells. Molecules bind together and break apart. Energy flows from one form to another. And through countless chemical transformations, inanimate matter becomes animate. Dead molecules become living organisms. Understanding what chemistry is required for life beyond Earth means understanding what makes life possible at all. The elements, the reactions, the solvents, and the energy sources that could allow chemistry to cross the threshold from complex but lifeless reactions into something that grows, reproduces, evolves, and ultimately builds civilizations among the stars. Carbon stands at the center of all known life. Every organism on Earth, from bacteria to blue whales, builds its body from carbon-based molecules. Carbon's unique properties make it extraordinarily suitable for life. Each carbon atom can form 4 chemical bonds with other atoms, allowing it to create an immense diversity of molecular structures, long chains, branching trees, rings, and complex 3-dimensional shapes. Carbon bonds with itself strongly enough to create stable molecules, but not so strongly that the bonds cannot be broken and rearranged through normal chemical reactions. This balance allows carbon molecules to be both stable enough to maintain structure and reactive enough to participate in the constant chemical transformations that life requires. Organic chemistry, the chemistry of carbon compounds, encompasses millions of known molecules and potentially billions more that could exist. Carbon combines readily with hydrogen, oxygen, nitrogen, sulfur, and phosphorus to create the molecules of life. Proteins, the workhorses of cells that catalyze reactions and build structures, are chains of amino acids linked together, each amino acid containing carbon, hydrogen, oxygen, and nitrogen. DNA and RNA, which store and transmit genetic information, are built from carbon-containing sugars, phosphate groups, and nitrogen-rich bases. Lipids, which form cell membranes and store energy, are long carbon chains with various functional groups attached. Carbohydrates, which provide energy and structural support, are carbon molecules with hydrogen and oxygen in specific ratios. But is carbon truly necessary for life, or is it simply the element that happened to work on Earth? Silicon, sitting directly below carbon in the periodic table, shares many of carbon's properties. Silicon also forms 4 chemical bonds and can create chains and rings similar to carbon. Science fiction has long speculated about silicon-based life, but silicon faces significant challenges. Silicon-silicon bonds are weaker than carbon-carbon bonds, making long silicon chains less stable. Silicon compounds tend to be much less diverse than carbon compounds. While carbon forms millions of different molecules, silicon chemistry is far more limited. Most critically, silicon's most common compound is silicon dioxide, quartz, sand, rock, which is extremely stable and insoluble. When silicon burns with oxygen, it creates solid rock rather than a gas that can be easily expelled and recycled. However, silicon-based life might be possible in environments completely unlike Earth. In extremely cold environments where water is frozen solid, silicon chemistry might become more favorable. In the presence of liquid hydrocarbons instead of water, silicon compounds might behave differently, remaining soluble and reactive rather than precipitating as rocks. A frigid world with seas of liquid methane or ethane, like Saturn's moon Titan, might provide conditions where silicon-based biochemistry could operate. Such life would function on completely different principles than Earth's carbon-based organisms, but it might still meet the basic requirements: complexity, self-replication, evolution, and metabolism. Hydrogen plays a crucial role in biochemistry beyond being part of organic molecules. Hydrogen ions, protons, are essential for energy generation in cells. Earth's organisms create differences in hydrogen ion concentration across membranes, then allow the ions to flow back through specialized proteins called ATP synthase, which harness the flowing ions to create ATP, the universal energy currency of life. This process, called chemiosmosis, powers nearly all life on Earth and represents a fundamental way of coupling energy sources to useful work. Any biochemistry, whether carbon-based or otherwise, would need some mechanism for capturing and storing energy, and hydrogen's simple chemistry makes it an excellent candidate for this role, regardless of the specific biochemistry involved. Oxygen serves multiple roles in Earth's biochemistry. It's part of water, part of most organic molecules, and it serves as the final electron acceptor in cellular respiration, the process by which organisms extract energy from food. When glucose is metabolized with oxygen, the reaction releases large amounts of energy that cells capture in the chemical bonds of ATP. This oxygen-based metabolism, called aerobic respiration, is far more efficient than metabolism without oxygen. However, oxygen was not always available on Earth. For the first 2 billion years or more, Earth's atmosphere contained very little free oxygen, and early life functioned without it, using anaerobic metabolism based on different chemical reactions. Some organisms today still live without oxygen, in deep ocean sediments or the guts of animals, using sulfur compounds, nitrates, or iron as alternatives to oxygen. Life beyond Earth might never develop oxygen-based metabolism if oxygen never becomes abundant in the atmosphere. Planets orbiting red dwarf stars might have difficulty accumulating oxygen because ultraviolet light from the star, which on Earth helps break apart water molecules in the upper atmosphere, leading to oxygen accumulation, is less intense. Life on such worlds might remain dependent on anaerobic metabolism indefinitely, which would likely limit the size and energy consumption of organisms. Active, energy-intensive lifestyles, like those of birds or mammals, require the high energy output that only oxygen metabolism provides. Alien life using alternative metabolic pathways might be restricted to smaller, slower, lower energy forms. Nitrogen is essential for proteins and nucleic acids. It's found in amino acids and in the bases that make up DNA and RNA. Nitrogen chemistry is complex and often difficult. Nitrogen gas in the atmosphere consists of 2 nitrogen atoms triple bonded together, making it very stable and unreactive. Converting atmospheric nitrogen into biologically useful forms, a process called nitrogen fixation, requires significant energy or specialized catalysts. On Earth, certain bacteria can fix nitrogen using enzymes containing iron and molybdenum. Lightning also fixes nitrogen by forcing nitrogen and oxygen to react in the high-energy conditions of electrical discharge. Life on other planets would need some source of biologically available nitrogen, either through similar fixation processes or through nitrogen already present in reactive forms. Phosphorus plays a unique and critical role in biochemistry. It's part of the backbone of DNA and RNA, linking the sugar molecules together into the long chains that store genetic information. It's also central to ATP, the molecule that stores and transfers energy in cells. Phosphate groups can be added to and removed from molecules to regulate their activity, serving as switches that turn cellular processes on and off. There is no obvious substitute for phosphorus in these roles. Unlike carbon, nitrogen, and oxygen, which are abundant in the universe, phosphorus is relatively rare, created only in certain types of stellar processes. A planet poor in phosphorus might struggle to develop complex life, at least of the kind we would recognize. Sulfur contributes to protein structure through disulfide bonds, connections between sulfur atoms in different parts of a protein that help the protein fold into its proper three-dimensional shape. Some organisms use sulfur compounds in their metabolism instead of or in addition to oxygen. Near hydrothermal vents on Earth's ocean floor, bacteria oxidize hydrogen sulfide, the compound that smells like rotten eggs, to generate energy. Entire ecosystems build on these chemosynthetic bacteria, demonstrating that sunlight and photosynthesis are not necessary for life. An alien world with extensive volcanic or hydrothermal activity could support life based on sulfur chemistry, even in complete darkness. Trace elements, though needed in tiny amounts, are essential for many biological processes. Iron is central to hemoglobin, the protein that carries oxygen in blood, and to many enzymes involved in energy metabolism. Magnesium sits at the center of chlorophyll molecules, enabling photosynthesis. Zinc, copper, manganese, and other metals serve as cofactors for enzymes, helping catalyze reactions that would otherwise proceed too slowly to sustain life. An alien biochemistry would likely require its own set of trace elements, perhaps using metals common on its world but rare on Earth, or finding entirely different solutions to catalysis and molecular structure. Water serves as the solvent for biochemistry on Earth, the medium in which all cellular chemistry occurs. Water has remarkable properties that make it ideal for life. It remains liquid across a wide temperature range, from 0 to 100 degrees Celsius at Earth's atmospheric pressure. It has a high heat capacity, meaning it resists temperature changes, which helps organisms maintain stable internal temperatures. Water molecules are polar, with a slight positive charge on one end and a slight negative charge on the other, allowing water to dissolve ionic compounds and interact with many different types of molecules. The hydrogen bonds between water molecules create surface tension, capillary action, and the unusual property that ice floats on liquid water, a characteristic that has profound implications for life in oceans and lakes. But is water necessary for life, or might other liquids serve as solvents for alternative biochemistries? Ammonia has been proposed as a possible alternative. Ammonia remains liquid at much colder temperatures than water. It freezes at -78 degrees Celsius and boils at -33 degrees Celsius at Earth's atmospheric pressure. A very cold planet, too cold for liquid water, might have lakes or oceans of liquid ammonia. Ammonia shares some of water's properties. It's polar, can form hydrogen bonds, and dissolves many substances. However, ammonia is a less effective solvent than water for many compounds, and the biochemistry that could operate in liquid ammonia would necessarily be very different from Earth's water-based life. Methane and ethane, though non-polar and very different from water, exist as liquids on Titan, Saturn's largest moon. Titan has lakes and rivers of liquid hydrocarbons on its surface, creating a hydrological cycle remarkably similar to Earth's water cycle, but operating at temperatures around -180 degrees Celsius. Could life exist in these hydrocarbon lakes? The chemistry would be completely unlike anything on Earth. Reactions that occur readily in water might not occur at all in methane, while entirely different reactions become possible. Cell membranes would need to be built from different molecules. The lipid membranes used by Earth cells wouldn't function in liquid methane. Energy metabolism would follow different pathways. But some scientists argue that the sheer strangeness of Titan's environment doesn't preclude life, only life that operates on unfamiliar principles. Supercritical fluids represent another possibility. Under high pressure and high temperature, substances enter a supercritical state where the distinction between liquid and gas breaks down. Supercritical carbon dioxide, for instance, behaves as both liquid and gas simultaneously, with properties of each. Deep beneath the surfaces of certain planets, conditions might create supercritical water or other supercritical fluids that could potentially serve as solvents for exotic biochemistries operating under extreme conditions. Energy sources drive all biochemistry. On Earth, sunlight powers most ecosystems through photosynthesis. Plants and photosynthetic bacteria capture light energy and use it to build organic molecules from carbon dioxide and water. These organic molecules then flow through food chains, ultimately providing energy for all other organisms. But many alternative energy sources exist. Chemical energy from redox reactions, where electrons transfer from one molecule to another, can sustain life in complete darkness. Radioactive decay in a planet's interior could provide steady energy through the heat it generates, potentially supporting life in subsurface environments for billions of years, even if the star above has long since died. The origin of life, the transition from complex chemistry to living organisms, requires conditions where organic molecules can form, concentrate, and begin the process of self-replication and evolution. On Earth, this might have occurred in tidal pools, in hydrothermal vents, in ice, or even in the atmosphere. The exact location and mechanism remain uncertain, but the chemistry required involves forming increasingly complex molecules from simpler precursors, eventually creating molecules capable of catalyzing reactions, including their own replication. This requires an energy source to drive uphill reactions that create complexity from simplicity, fighting against entropy. It requires some form of containment, membranes or surfaces, to concentrate molecules and create distinct chemical environments. And it requires time for random chemical processes to explore countless possibilities until self-replicating systems emerge. The universality of certain chemical principles suggests that life elsewhere, no matter how alien, would still obey the same rules of chemistry and thermodynamics that govern Earth's life. All life must extract energy from its environment and use that energy to create and maintain complex organization. All life must reproduce, passing information to offspring. All life must evolve through variation and selection. These requirements constrain the chemistry of life, regardless of what specific molecules are involved. Carbon is not the only possible basis for complex chemistry, water is not the only possible solvent, and oxygen is not the only possible energy source, but any living system must solve the same fundamental chemical problems: how to capture and store energy, how to build complex molecules, how to replicate information, and how to maintain organization in a universe that constantly tends toward disorder. The chemistry required for life beyond Earth encompasses the familiar carbon, water, proteins, and DNA, and the exotic silicon biochemistry in hydrocarbon seas, life in supercritical fluids, using metals we've never heard of, organisms metabolizing on reactions we've never imagined. The universe provides the raw materials everywhere: hydrogen from the Big Bang, heavier elements forged in stars and scattered through supernova explosions. Every planet, moon, and asteroid contains chemistry, happening constantly through radiation, temperature gradients, and the simple mixing of different compounds. Whether that chemistry crosses the threshold into life depends on having the right combination of elements, solvents, energy sources, and time, ingredients that might exist on countless worlds throughout the cosmos, waiting for chemistry to become biology in endless variations on the theme of life. The solar wind that flows through space. From the surface of the sun, an invisible river flows outward in all directions, streaming past the planets and extending far beyond the orbit of Pluto into the distant reaches of the solar system. This is the solar wind, a continuous flow of charged particles, primarily electrons and protons, that escape from the sun's outer atmosphere and race through space at speeds ranging from 250 to over 500 miles per second. This wind carries with it pieces of the sun itself, along with magnetic fields that thread through the solar system, creating an enormous bubble of solar influence that shapes the space environment around every planet. The story of the solar wind begins in the sun's corona, the outermost layer of the solar atmosphere that extends millions of miles above the visible surface. The corona is paradoxically much hotter than the surface below it, while the sun's visible surface, the photosphere, has a temperature of about 10,000 degrees Fahrenheit. The corona reaches temperatures exceeding 2 million degrees. This extreme heating, still not completely understood, but likely involving magnetic fields and wave energy, gives particles in the corona so much energy that many of them move faster than the sun's escape velocity. Imagine standing at the sun's surface and throwing a baseball upward. To escape the sun's gravity, you would need to throw it at about 380 miles per second. In the corona, thermal energy heats particles to such extreme temperatures that a significant fraction of them are moving faster than this escape velocity. These particles don't fall back to the sun, they stream away into space, carrying energy and momentum with them. The sun is essentially evaporating, losing mass continuously through this process, though at a rate so slow that it would take trillions of years to evaporate completely. The solar wind is not uniform. It flows faster from some regions of the sun than others, creating a complex structure as it expands outward. Above the sun's equatorial regions, where magnetic field lines tend to loop back to the surface, the solar wind emerges more slowly, typically around 250 miles per second. But at the sun's poles and in coronal holes, regions where magnetic field lines extend far into space, rather than looping back, the wind flows much faster, reaching speeds of 500 miles per second or more. These variations in speed create interaction regions where fast solar wind catches up to slow solar wind. Imagine cars on a highway where fast-moving traffic overtakes slower-moving traffic. The fast solar wind compresses the slow solar wind ahead of it, creating regions of enhanced density and magnetic field strength. These co-rotating interaction regions, named because they rotate with the sun as it spins, sweep through the solar system like a spiral pattern, buffeting planets with alternating streams of slow and fast wind. As the solar wind flows outward, it carries the sun's magnetic field with it. The magnetic field lines become stretched and twisted, creating a spiral pattern much like water from a rotating garden sprinkler. This interplanetary magnetic field threads through the entire solar system, connecting magnetically active regions on the sun to the distant reaches of space. When magnetic field lines from different regions of the sun come together, in space they can reconnect, releasing energy and accelerating particles to even higher speeds. The solar wind is not just a steady breeze but includes violent gusts and storms. When an eruption occurs on the sun, a solar flare or a coronal mass ejection, enormous quantities of plasma and magnetic field can be hurled into space far faster than the normal solar wind. A coronal mass ejection can contain billions of tons of material moving at speeds up to several thousand miles per second. When one of these structures reaches Earth, typically 1 to 3 days after leaving the sun, it can compress Earth's magnetic field, trigger spectacular auroras, and potentially disrupt satellites, power grids, and communication systems. The journey of a solar wind particle from the sun to Earth takes about 4 to 5 days travelling at typical speeds. During this journey, the particle encounters very little. Space between the sun and Earth is remarkably empty. A cubic inch of the solar wind near Earth contains only about 5 to 10 protons, far more tenuous than even the best vacuum we can create in laboratories on Earth. Yet despite this extreme sparseness, the solar wind carries significant momentum and energy simply because of the vast volume through which it flows and the speeds at which it travels. When the solar wind encounters a planet, what happens depends on whether that planet has a magnetic field. Earth's magnetic field creates a protective bubble called the magnetosphere that deflects most of the solar wind around the planet. The interaction is dynamic and complex. The leading edge of Earth's magnetosphere, called the bow shock, is where the supersonic solar wind first encounters Earth's magnetic field and slows down abruptly, much like air piling up in front of a supersonic aircraft creates a shock wave. This shock heats the solar wind and diverts it around Earth's magnetosphere, creating a turbulent boundary layer called the magnetosheath. Some solar wind particles do manage to penetrate into Earth's magnetosphere, particularly when reconnection occurs between the interplanetary magnetic field and Earth's magnetic field. These particles get funneled along Earth's magnetic field lines toward the polar regions, where they collide with atoms in the upper atmosphere, creating the shimmering curtains of light we call auroras. The green and red colours come from oxygen atoms at different altitudes being excited by these collisions, while nitrogen produces blue and purple hues. Planets without magnetic fields like Mars and Venus experience the solar wind very differently. Without a protective magnetic bubble, the solar wind interacts directly with the upper atmosphere. Over millions of years, this interaction strips away atmospheric particles, carrying them off into space. Mars, which once had a thicker atmosphere and possibly liquid water on its surface, has lost much of its atmosphere to this process. The solar wind literally peels away the outer layers of the Martian atmosphere, particularly during strong solar storms, gradually transforming Mars from a potentially habitable world to the thin, dry atmosphere we observe today. The Moon, with neither atmosphere nor magnetic field, receives the full force of the solar wind directly on its surface. Solar wind particles impact the lunar regolith, becoming implanted in the soil. Over billions of years, this process has altered the chemistry and appearance of the lunar surface, darkening it and creating what scientists call space weathering. Ancient lunar rocks brought back by Apollo astronauts contain trapped solar wind particles that serve as a record of how the Sun's output has changed over time. Giant planets like Jupiter and Saturn have enormous magnetospheres that extend millions of miles into space. Jupiter's magnetosphere is so large that if we could see it from Earth, it would appear several times larger than the full moon in the sky. The solar wind compresses these magnetospheres on the side facing the Sun and stretches them into long tails on the night side. Within these giant magnetospheres, the interaction between the solar wind, the planet's magnetic field, and particles from the planet's moons creates some of the most intense radiation environments in the solar system. The solar wind doesn't flow forever. Far from the Sun, billions of miles beyond the orbits of the planets, it begins to slow down as it encounters the interstellar medium, the dilute gas and plasma that fills the space between stars. The Voyager spacecraft, launched in 1977, have travelled far enough to cross the boundary where the solar wind slows to subsonic speeds, called the termination shock. This boundary is not spherical, but is pushed outward in the direction the solar system is moving through the galaxy and compressed in the opposite direction. Beyond the termination shock lies a region called the heliosheath, where the solar wind has slowed but still moves outward, compressed and heated by its interaction with the interstellar medium. The exact shape and extent of this region depend on the strength of the solar wind and the pressure of the interstellar medium outside. Voyager 1 and Voyager 2 have now crossed even farther, passing through the heliopause, the outer boundary where the solar wind effectively stops and interstellar space begins. They are now in a region where the dominant flow is no longer from the Sun, but from the galaxy itself. The structure created by the solar wind, this vast bubble of solar influence, extending billions of miles in all directions, is called the heliosphere. It serves as a partial shield, deflecting some of the cosmic rays that stream through the galaxy. Without this protection, the flux of high-energy particles reaching the inner solar system would be higher, potentially affecting planetary atmospheres and creating more radiation hazards for any life on planetary surfaces. The solar wind varies with the sun's activity cycle. During solar maximum, when the sun is most active with many sunspots and frequent eruptions, the solar wind is stronger, more variable, and more likely to include fast-moving coronal mass ejections. During solar minimum, when the sun is quieter, the wind becomes more regular, though still continuous. This 11-year cycle affects space weather throughout the solar system, influencing everything from auroral activity on Earth to the radiation environment encountered by spacecraft. The composition of the solar wind provides a sample of the sun's outer layers. While predominantly hydrogen, both protons and electrons, the wind also contains helium, making up about 4% of the particles, along with trace amounts of heavier elements, like carbon, nitrogen, oxygen, neon, magnesium, silicon, and iron. These heavier elements are present in much smaller quantities but provide valuable information about solar composition and the processes occurring in the corona. Different types of solar wind have different characteristics. The slow solar wind is denser and cooler, while the fast wind is more tenuous but carries more kinetic energy due to its higher speed. Transient events like coronal mass ejections create temporary structures in the solar wind with dramatically enhanced density, speed, and magnetic field strength. These variations create a constantly changing space environment that spacecraft and planets must navigate. The solar wind also carries information outward from the sun. Disturbances created by solar activity propagate through the solar wind, and by observing how these disturbances evolve and interact as they move through space, scientists can learn about the properties of the wind itself and the magnetic fields threading through it. Spacecraft throughout the solar system serve as sentinels, measuring the solar wind's properties at different locations and providing a three-dimensional view of how this invisible river flows through our cosmic neighborhood. Every star produces a stellar wind, analogous to our solar wind, and these winds play important roles in stellar evolution and in shaping the environments around other planetary systems. Hot, massive stars produce fierce stellar winds that can carry away significant fractions of the star's mass over its lifetime. Cool, evolved stars like red giants produce slower but denser winds. Understanding our own solar wind provides insights into these stellar winds throughout the galaxy, connecting the processes occurring in our immediate space environment to the broader evolution of stars and planetary systems across the universe. The invisible forces holding galaxies together. When you look at a photograph of a spiral galaxy, you see a beautiful pinwheel of stars, gas, and dust rotating around a central bulge. The image suggests a structure held together by visible matter, the billions of stars whose light creates the galaxy's luminous form. But appearances are deceiving. The forces actually holding galaxies together are largely invisible, operating through mechanisms both understood and mysterious. Gravity binds these cosmic structures, but most of the mass providing that gravity cannot be seen, cannot be detected except through its gravitational effects, and remains one of the deepest mysteries in astrophysics. The first clue that something invisible was holding galaxies together came from studying how stars move within them. In the 1970s, astronomer Vera Rubin conducted detailed observations of spiral galaxies, measuring the velocities of stars and gas clouds at various distances from the galactic centers. According to Newton's laws of motion and gravity, objects farther from the center of mass should orbit more slowly, just as Neptune orbits the Sun much more slowly than Mercury. The visible matter in galaxies is concentrated toward the center, with the brightness falling off dramatically in the outer regions. Based on this distribution of visible matter, stars in the outer parts of galaxies should be moving much slower than stars near the center. But that's not what Rubin found. Instead, the rotation curves, graphs showing orbital velocity versus distance from the center, were flat. Stars in the outer regions were moving just as fast as stars closer to the centre, sometimes even faster. This could only mean one thing. There was far more mass in these galaxies than could be accounted for by visible stars, gas and dust. This additional mass had to extend well beyond the visible disk, forming a massive spherical halo surrounding each galaxy. The nature of this dark matter remains unknown, but its gravitational effects are undeniable. Galaxies are embedded within dark matter halos that contain several times more mass than all the visible matter combined. A typical spiral galaxy, like the Milky Way, might contain about 100 billion solar masses of visible matter, stars, gas, dust, planets, but resides within a dark matter halo containing perhaps 1 trillion solar masses. This dark matter halo extends perhaps 10 times farther than the visible disk, creating a gravitational well that holds the galaxy together. Dark matter doesn't interact with light. It neither emits, absorbs, nor reflects electromagnetic radiation of any wavelength. It interacts with normal matter almost exclusively through gravity. This makes it invisible to telescopes, but reveals its presence through gravitational effects. The flat rotation curves that Rubin observed were the first clear evidence, but dark matter reveals itself in other ways as well. Gravitational lensing provides some of the most compelling evidence for dark matter in and around galaxies. According to Einstein's general theory of relativity, mass warps spacetime, and light follows the curves in that warped geometry. When light from a distant galaxy passes near a massive object, its path bends. By measuring this bending and calculating how much mass would be needed to produce it, astronomers can map the distribution of mass, including dark matter. These mass maps show that dark matter is distributed in huge halos around galaxies, exactly as predicted from rotation curve studies. The bullet cluster provides particularly dramatic evidence. This structure formed when two galaxy clusters collided and passed through each other. During the collision, the hot gas from each cluster, normal matter that can interact with itself, slowed down and remained near the collision site, heated by the impact. But gravitational lensing maps show that most of the mass is not where the gas is. Instead, it separated from the gas and continued moving with the galaxies themselves. This separated mass must be dark matter, which doesn't collide or interact with normal matter except through gravity, passing right through during the cluster collision. The gravitational force from dark matter operates according to Newton's law of universal gravitation for most purposes, though general relativity provides the more accurate description, especially in strong gravitational fields. The force is proportional to the product of the masses and inversely proportional to the square of the distance between them. Even though individual dark matter particles don't clump together the way atoms do, they can't radiate energy and settle into compact structures. Collectively, they form halos through gravitational attraction, with each particle orbiting in the combined gravitational field of all the others. These dark matter halos formed before the visible galaxies themselves. In the early universe, dark matter could begin collapsing into clumps earlier than normal matter, because dark matter doesn't interact with radiation. Normal matter, coupled to photons in the early universe, couldn't collapse efficiently until after recombination, when electrons combined with nuclei to form neutral atoms and the universe became transparent. By that time, dark matter had already created gravitational wells, regions of enhanced density, and normal matter fell into these wells, forming the first galaxies within the scaffolding of dark matter structure. Computer simulations of galaxy formation must include dark matter to reproduce the observed properties of galaxies. Simulations using only normal matter produce galaxies that look nothing like what we observe. But when dark matter is included, with properties consistent with observations, non-interacting except through gravity, with a specific abundance relative to normal matter, The simulations produce galaxies remarkably similar to real ones, with flat rotation curves, realistic sizes, and appropriate clustering properties. The dark matter distribution within galaxies follows a characteristic profile. The density is highest at the center and decreases toward the outer regions, but much more gradually than the distribution of visible matter. Various mathematical models describe this distribution, with names like the NFW profile, named after Julio Navarro, Carlos Frenk, and Simon White, who studied dark matter halos in simulations in the 1990s. These profiles predict specific density distributions that can be tested against observations through rotation curves and gravitational lensing. But dark matter isn't the only force holding galaxies together. Gravity from visible matter contributes as well, though less than dark matter. The combined gravitational pull from billions of stars, gas clouds, dust, and the supermassive black hole at the center all help bind the galaxy. The distribution of this visible matter creates the gravitational potential in which stars orbit, and while dark matter dominates the total mass, the visible matter shapes the inner regions where most stars reside. Orbital mechanics plays a crucial role in keeping galaxies stable. Each star orbits in the combined gravitational field of all other matter in the galaxy, both visible and dark. Stars don't simply circle the galactic center in perfect circles like planets orbiting the Sun. Their orbits are more complex, elliptical, and tilted at various angles, creating the three-dimensional structure of the galaxy. In spiral galaxies, the disk forms because stars that were born from a rotating cloud of gas inherited that rotation, and collisions between gas particles dissipated energy and flattened the distribution into a disk. The supermassive black hole at the center of most galaxies contributes to holding the inner regions together, though its mass is typically small compared to the total galaxy mass, perhaps 0.1 to 1% of the bulge mass. The black hole at the center of the Milky Way, Sagittarius A star, contains about 4 million solar masses. While this is enormous by any terrestrial standard, it's tiny compared to the Milky Way's total mass of perhaps 1 trillion solar masses, including dark matter. The black hole's gravitational influence dominates only in the innermost few light years. Spiral density waves also play a role in galactic structure, though they're not forces holding the galaxy together in the same sense as gravity. These waves are regions of enhanced density that rotate through the disk, compressing gas and triggering star formation. The spiral arms we see are not fixed structures, with the same stars always in them, but rather patterns that rotate at a different speed than the stars themselves. Stars move in and out of the spiral arms as they orbit, spending more time in the arms where the density is higher, creating the appearance of persistent spiral structure. Galaxy clusters add another layer of complexity. Galaxies themselves are held together primarily by their dark matter halos, but galaxies cluster together in groups and clusters, which are themselves held together by even larger dark matter halos. The Milky Way is part of the local group, which includes the Andromeda Galaxy and about 50 smaller galaxies, all orbiting within a common dark matter halo. Galaxy clusters, like the Virgo cluster, contain thousands of galaxies within a massive dark matter halo containing quadrillions of solar masses. The dynamical state of galaxies, whether they're stable, expanding, or contracting, depends on the balance between kinetic and potential energy. If the kinetic energy of all the stars and gas exceeds twice the magnitude of the gravitational potential energy, the galaxy would be unbound and would eventually fly apart. The fact that galaxies remain bound over billions of years tells us that they're in virial equilibrium, a state where kinetic and potential energy are balanced according to the virial theorem. This relationship allows astronomers to estimate the total mass of galaxies from observations of how fast their contents are moving. Some alternative theories propose that dark matter doesn't exist, and that instead, our understanding of gravity needs modification. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983, suggests that gravity behaves differently at very low accelerations, like those experienced by stars in the outer regions of galaxies. MOND can reproduce flat rotation curves without dark matter, but it struggles to explain other observations like gravitational lensing and the bullet cluster. Most physicists consider dark matter more likely to be a new type of particle rather than a modification of gravity, though the question remains open until dark matter is directly detected or conclusively ruled out. The search for dark matter particles continues in laboratories around the world. Experiments deep underground attempt to detect rare interactions between dark matter particles and normal matter. Other experiments search for signals of dark matter particles annihilating with each other or decaying into detectable particles. The Large Hadron Collider attempts to create dark matter particles in high-energy collisions. So far, no experiment has definitively detected dark matter particles, but each null result constrains the possible properties of dark matter, narrowing the possibilities. The invisible forces holding galaxies together operate on timescales of hundreds of millions to billions of years. A star near the Sun's position in the Milky Way takes about 225 million years to complete one orbit around the galactic center. During this time, the combined gravitational pull from the dark matter halo, the visible matter in the disk and bulge, and all other components keeps the star bound to the galaxy. The stability of this configuration over billions of years, galaxies don't fly apart, they maintain their structures over cosmic time, testifies to the power and precision of the gravitational forces at work. Understanding the invisible forces holding galaxies together remains one of the central challenges in astrophysics. The existence of dark matter is now accepted by most scientists based on the overwhelming gravitational evidence, but its fundamental nature remains mysterious. Whether it consists of weakly interacting massive particles, axions, primordial black holes, or something entirely unexpected, dark matter's gravitational pull provides the invisible glue that holds galaxies together, shapes their structure, determines their evolution, and creates the cosmic web of large-scale structure that defines the universe on the largest scales, making dark matter's invisibility one of the most tantalizing mysteries in science, a substance that makes up most of the universe's mass, but reveals itself only through the ancient and universal force of gravity that governs the motion of everything, from falling apples to orbiting galaxies. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival. In boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond. In volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of Barophil's pressure-loving organisms suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter. though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environment can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds, where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome. Given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe. The glowing clouds, where stars are born. Scattered throughout the galaxy are vast clouds of gas and dust, some spanning hundreds of light years across, glowing with ethereal colours against the darkness of space. These nebulae are the cosmic nurseries where stars come into being, regions where the raw materials of the universe, hydrogen and helium from the Big Bang, mixed with heavier elements forged in previous generations of stars, gather, collapse, and ignite into new points of light. Understanding these stellar nurseries means understanding one of the most fundamental processes in the cosmos, the transformation of diffuse gas into concentrated spheres of nuclear fusion that will shine for millions or billions of years. The process begins with the molecular cloud, a region of space where gas has accumulated and cooled to temperatures only a few degrees above absolute zero. These clouds are dark when viewed in visible light because the dust mixed with the gas blocks starlight from behind, creating dark patches against the background glow of the Milky Way. But observe them in infrared or radio wavelengths, and they reveal intricate structures, filaments, cores, and clumps where the density varies, creating a complex web of material threaded throughout these regions. Molecular clouds are mostly hydrogen, but at the low temperatures found within them, individual hydrogen atoms have paired up to form molecular hydrogen, H2. This molecular form is more stable at cold temperatures, and these clouds also contain molecules that might seem surprising in the depths of space: carbon monoxide, water, ammonia, formaldehyde, and even more complex organic molecules. The chemistry occurring in these cold clouds is rich and varied, with molecules forming on the surfaces of dust grains and in the gas phase, building up a diverse molecular inventory over millions of years. Something must disturb these clouds to initiate star formation. A cloud can exist in a stable state for a long time, with internal pressure from the gas supporting it against its own gravity. But if the cloud is compressed, if its density increases beyond a critical threshold, gravity begins to win. This compression can come from several sources: a shockwave from a nearby supernova explosion, pushing through space, the compression created when spiral arms of the galaxy pass through the region, or even the radiation and winds from existing massive stars that can trigger collapse in adjacent cloud material. Once collapse begins, the cloud fragments into smaller pieces. A single large molecular cloud doesn't collapse into one giant star. Instead, it breaks apart into hundreds or thousands of individual collapsing cores, each one potentially forming a star or a small system of stars. This fragmentation occurs because as the cloud collapses, it develops instabilities. Regions that are slightly denser collapse a bit faster, pulling in material from their surroundings, and these growing density enhancements become the seeds of individual stars. Picture one of these collapsing cores. Initially, it might be 1/10 of a light year across, containing perhaps a few times the mass of our Sun, with a density barely above that of the surrounding cloud. As it contracts under its own gravity, the material falls inward, but it doesn't fall uniformly. The core rotates slowly, inherited from the overall rotation of the cloud, and as it contracts, conservation of angular momentum causes it to spin faster, just as a figure skater spins faster when pulling their arms inward. This rotation prevents all the material from falling directly onto the forming star at the center. Instead, material settles into a rotating disk around the protostar, a flattened structure where gas and dust orbit the central condensation. This is a protoplanetary disk, the structure from which planets will eventually form. The material in this disk gradually spirals inward, losing angular momentum through viscosity and magnetic effects, feeding the growing protostar at the center, while the outer portions of the disk may remain in orbit for millions of years. As the protostar grows, accumulating more and more mass from the infalling material, its center heats up. Gravitational potential energy converts to thermal energy as material falls inward, and the temperature and pressure at the core climb steadily. The protostar begins to glow, first emitting infrared radiation, then gradually becoming brighter as it contracts. At this stage, it's not yet a true star. No nuclear fusion occurs at its core, but it's radiating energy produced by gravitational contraction, a process called Kelvin-Helmholtz contraction. The infalling material doesn't simply accumulate smoothly. Young protostars are violent, turbulent objects. They generate powerful magnetic fields that interact with the surrounding disk and the infalling gas. These magnetic fields can launch jets, narrow streams of gas that shoot outward from the poles of the protostar at speeds of hundreds of miles per second. These jets plow into the surrounding molecular cloud, creating bow shocks where they collide with the ambient gas, heating it and causing it to glow. These glowing regions, called Herbig-Haro objects, appear as bright knots and filaments near young stars, moving visibly over periods of years as the jets evolve and push through the surrounding gas. The jets serve an important function. They carry away angular momentum and energy, allowing material in the disk to continue falling onto the protostar. Without this mechanism to remove angular momentum, the disk would simply spin faster and faster, and accretion would halt. The protostar continues to accrete material and contract for hundreds of thousands to millions of years, depending on its mass. During this time, it's deeply embedded in the cloud that spawned it, hidden from view at visible wavelengths by the cocoon of gas and dust surrounding it. Infrared observations can penetrate this obscuration, revealing the glowing protostar and its disk within the dark cloud. These embedded protostars mark the earliest visible stages of star formation, objects that are still gaining mass and have not yet ignited nuclear fusion. Eventually, the temperature and pressure at the protostar's core reach a critical threshold, typically around 10 million degrees. At this point, protons begin to fuse, creating helium and releasing energy through nuclear fusion. The protostar becomes a true star, entering what's called the main sequence, where it will spend the majority of its life fusing hydrogen into helium. The energy released by fusion creates an outward pressure that finally halts the gravitational contraction, and the star settles into a stable configuration where gravity and pressure are balanced. When the star ignites, it begins to affect its surroundings dramatically. The radiation from the young star heats the surrounding gas and dust, Ultraviolet light from the star ionizes hydrogen atoms, stripping electrons away and creating a region of ionized gas called an H2 region. These ionized regions glow with a characteristic reddish-pink color, the result of electrons recombining with protons and cascading down through energy levels, emitting light at specific wavelengths. This is the glow we see in many famous nebulae: the Orion Nebula, the Eagle Nebula, the Lagoon Nebula, vast regions of ionized gas illuminated by the intense radiation from young hot stars. If the star is particularly massive and hot, more than about 8 times the Sun's mass, it produces copious ultraviolet radiation that can ionize gas over large volumes of space. A single massive star can create an H2 region spanning dozens of light years. Multiple massive stars forming in the same region create even larger ionized bubbles. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, glows because of a handful of massive young stars at its center, whose radiation ionizes the surrounding molecular cloud. The radiation pressure and stellar winds from young stars don't just make the cloud glow, they also begin to push the gas away, clearing out cavities in the molecular cloud. This feedback can actually trigger more star formation in the surrounding material. As the expanding HII region compresses gas at its edges, it can push that material above the density threshold needed for collapse, triggering new rounds of star formation in a process that propagates through the cloud. Young star clusters often show evidence of sequential star formation, with the oldest stars at the center surrounded by progressively younger stars farther out. The initial generation of stars alters the cloud, compressing and heating gas at the periphery, triggering the formation of the next generation. This process continues until the cloud is either dispersed entirely by the radiation and winds from the young stars, or exhausted of material dense enough to form new stars. The most massive stars, those dozens of times more massive than the Sun, live brief but spectacular lives. They burn through their nuclear fuel in just a few million years, and then explode as supernova, catastrophic events that briefly outshine entire galaxies. These explosions inject tremendous energy into the surrounding gas, heating it to millions of degrees, accelerating it to thousands of miles per second, and enriching it with heavy elements created in the star and in the supernova explosion itself. Carbon, oxygen, silicon, iron, and even heavier elements like gold and uranium. These heavy elements mix into the molecular cloud, changing its composition. The next generation of stars that forms from this enriched material will contain more heavy elements than the previous generation. This process of stellar birth, life, death, and rebirth has been occurring for over 13 billion years, gradually enriching the interstellar medium with heavy elements. The earliest stars in the universe formed from nearly pure hydrogen and helium. Stars forming today, including our Sun, contain about 2% heavy elements by mass, a small fraction, but crucial for the formation of planets, and ultimately for the existence of life. The dust mixed throughout these star-forming clouds plays a crucial role beyond just blocking light. The tiny grains, typically less than a micrometer in size, serve as surfaces where molecules can form. Hydrogen atoms landing on a grain's surface can find each other and bond, forming molecular hydrogen far more efficiently than they could in the gas phase. Water molecules, carbon monoxide, and more complex organics also form on grain surfaces, then evaporate back into the gas or become incorporated into forming stars and planets. Star formation is not perfectly efficient. Only a small fraction of the gas in a molecular cloud, perhaps 1 to 10%, actually ends up in stars. The rest is either dispersed by stellar feedback, ejected by stellar winds and supernova explosions, or simply never reaches densities high enough to collapse. The molecular clouds we observe are continuously evolving, with some regions collapsing to form stars while other regions are being cleared out by the very stars that recently formed within them. Different regions of the galaxy have different rates of star formation. The spiral arms, where gas is compressed as it enters these density waves, show enhanced star formation, lighting up with the blue glow of young hot stars and the red emission from H2I regions. The galactic center, with its extreme environment and powerful tidal forces, has intense star formation, but also extreme feedback that can suppress star formation. The outer regions of the galaxy, with less gas available, form stars more slowly. Star formation is occurring right now throughout the Milky Way and throughout the universe. In distant galaxies, billions of light years away, we observe intense starbursts where entire regions of galaxies are forming stars at rates thousands of times higher than in our galaxy, triggered by galaxy collisions or mergers that compress enormous quantities of gas. The stars forming in those distant galaxies emit light that has travelled across most of the universe's history to reach our telescopes, showing us star formation as it occurred when the universe was much younger. The glowing nebulae we see in telescopes and photographs are not static monuments, but dynamic regions of ongoing transformation. The clouds are collapsing, the protostars are growing, the newly formed stars are dispersing the clouds that gave them birth. Within a few million years, the blink of an eye on cosmic timescales, a star-forming region transforms from a dark molecular cloud to a bright cluster of young stars, to a dispersed association of stars gradually spreading through the galaxy, each one carrying forward the legacy of its birth, enriching future generations of clouds with the elements created during its life, continuing the cycle of stellar birth and death that has shaped the galaxy since its formation billions of years ago. The different types of habitable planets. When astronomers speak of habitable planets, they often mean worlds similar to Earth, rocky planets with liquid water on their surfaces, orbiting at comfortable distances from sun-like stars. But the discovery of thousands of exoplanets over the past few decades has revealed that planetary systems come in astonishing variety, with planet types that don't exist in our solar system and orbital configurations that defy early expectations. This diversity suggests that habitability, the capacity to support life, might extend far beyond Earth-like worlds to encompass planet types that seem alien at first glance, yet might provide suitable conditions for life to emerge and thrive. Understanding the different types of habitable planets means expanding our definition of habitability beyond the familiar, to consider the full range of worlds where biology might find a foothold. Ocean worlds represent perhaps the most common type of potentially habitable planet. These are planets covered entirely or nearly entirely by deep oceans, with no dry land or only minimal landmass protruding above water. Earth itself is an ocean world to some degree, with about 70% of its surface covered by water, but true ocean worlds might have water covering 95 or even 100% of the surface, with global oceans potentially hundreds of kilometers deep. Such worlds might form beyond the snowline in their stellar systems, where water ice is abundant during formation, then migrate inward to warmer regions where the ice melts, creating global oceans. Life on ocean worlds might never develop terrestrial forms. Everything would evolve in water, from microscopic plankton to potentially large swimming organisms analogous to whales. Without land, there would be no forests, no land animals, no terrestrial plants. But aquatic life could still be extraordinarily diverse and complex. The key question for ocean worlds is whether photosynthetic life could evolve. Sunlight penetrates only the upper layers of water, so photosynthesis would be restricted to the surface zone. Below a certain depth, life would depend on organic matter sinking from above, or on chemical energy from hydrothermal vents on the ocean floor, much like deep-sea ecosystems on Earth. Extremely deep oceans present another challenge: high-pressure ice. At depths exceeding several hundred kilometers, pressure can become so intense that water freezes despite high temperatures, forming exotic ice structures called Ice 6, Ice 7, and other high-pressure phases that are denser than liquid water. A planet with oceans deep enough to reach these pressures would have a layer of exotic ice separating the liquid ocean from the rocky mantle below. This ice layer would prevent direct contact between water and rock, potentially limiting the availability of minerals and nutrients dissolved from rock that life might need. However, the ice itself might crack due to tidal forces or internal heat, allowing some exchange between the rocky interior and the ocean. Desert planets represent the opposite extreme, worlds where water is scarce, with most of the surface covered by deserts, sand dunes, or bare rock. These planets orbit closer to the inner edge of the habitable zone, where temperatures are higher and water is more likely to evaporate. Any water present might be concentrated in polar ice caps, in subsurface aquifers, or in rare oases where geological features trap moisture. Mars represents a partial example, a cold desert world where water exists mostly as ice, or locked in minerals, with liquid water appearing only occasionally in specific locations. Life on desert planets would need extreme water conservation strategies. Organisms might be active only during rare rain events, spending most of their time dormant. They might extract water from humidity in the air or from chemical reactions rather than drinking liquid water. They might have impermeable skins to prevent water loss, and highly efficient kidneys or equivalent organs that recycle water internally. Plant analogues might photosynthesize only at night when temperatures drop and humidity rises, closing all pores during the day to prevent water loss. Despite the harsh conditions, life could potentially thrive in sheltered microenvironments, shaded canyons, caves where humidity condenses, or underground where water from ancient aquifers remains accessible. Eyeball planets emerge around red dwarf stars when planets become tidally locked, always showing the same face to their star, with one hemisphere in permanent daylight and the other in eternal darkness. The day side receives constant intense heating, potentially creating a hot desert. The night side, receiving no sunlight, freezes solid. But at the terminator, the boundary between day and night, a ring of habitable conditions might exist where temperatures remain moderate. This ring might harbour a circular ocean, the eyeball, surrounded by ice on one side and desert on the other, creating a narrow band where life could flourish. Life on eyeball planets would be restricted to this habitable ring, adapted to conditions that never change. No day-night cycle, no seasons, just constant twilight with the star permanently fixed at the horizon. Organisms might spread around the entire circumference of the planet along this habitable band, but they couldn't expand toward either pole. Moving toward the substellar point would lead to lethal heat. Moving toward the antistellar point would lead to frozen darkness. The planet's climate would feature constant winds as air heated on the day side rises and flows toward the cold night side, creating atmospheric circulation patterns completely unlike Earth's weather. Super-Earths, rocky planets more massive than Earth, but less massive than Neptune, might be the most common type of habitable planet in the galaxy, despite having no analogue in our solar system. These worlds, with masses ranging from about 2 to 10 times Earth's mass, would have stronger surface gravity than Earth. An organism on a super-Earth twice Earth's mass might weigh twice what it would on Earth, creating challenges for movement and structural support, but super-Earths have potential advantages for habitability. Their stronger gravity can hold thicker atmospheres more effectively, providing better greenhouse warming and allowing habitable zones to extend farther from their stars. They might have more active plate tectonics due to greater internal heat, helping regulate climate over geological time. Life on super-Earths would likely evolve shorter, stockier body plans to cope with high gravity. Trees might be shorter and thicker. Animals might have more legs or stronger, thicker legs to support their weight. Flight might be more difficult, requiring more powerful wings and muscles. But the thicker atmosphere might actually make flight easier by providing more air resistance, potentially allowing organisms to evolve gliding or flying capabilities using less energy than on Earth, despite the higher gravity. Mini-Neptunes, planets with substantial hydrogen-helium atmospheres surrounding rocky or icy cores, represent a planet type between rocky super-Earths and gas giants. These worlds might not be habitable at their cloud tops where temperatures and pressures are moderate, but atmospheres are thick hydrogen-helium mixtures. However, some mini-Neptunes might have layers within their atmospheres where temperature and pressure allow water vapor to condense into liquid water droplets, creating water clouds and potentially habitable conditions within the atmosphere itself. Aerial life in these water clouds, floating organisms that never touch solid ground because there is no solid ground accessible, might evolve. Such organisms would need to regulate their buoyancy, perhaps using gas-filled bladders similar to fish swim bladders. They might extract nutrients from atmospheric chemistry or from particles suspended in the atmosphere. Reproduction might involve releasing spores or offspring that drift through the atmosphere until they find suitable conditions to grow. The entire biosphere would be three-dimensional and airborne, with no connection to any surface. Hycean worlds, a term combining hydrogen and ocean, represent a recently proposed planet type that might be surprisingly common and habitable. These are large planets with hydrogen-rich atmospheres and liquid water oceans beneath them, potentially including some mini-Neptunes if conditions are right. The thick hydrogen atmospheres would create greenhouse warming that keeps water liquid even at large distances from the star. Life on Hycean worlds would live in the oceans beneath kilometers of hydrogen atmosphere, never exposed to space but potentially able to thrive in the dark, high-pressure water below. The discovery of biosignatures on Hycean worlds might be easier than on Earth-like planets because their larger sizes and extended atmospheres make spectroscopic analysis more favourable. If life produces gases that reach the hydrogen atmosphere, methane, dimethyl sulfide, or other organic compounds, these might be detectable even with current telescope technology. Hycean worlds thus represent prime targets for near-term biosignature searches. Carbon planets might form in regions of protoplanetary disks, where carbon is more abundant relative to oxygen than in our solar system. Instead of being dominated by silicate minerals like Earth, these worlds might have surfaces and interiors rich in graphite, diamond, silicon carbide, and other carbon compounds. The chemistry of such worlds would be radically different from Earth's. Oceans might consist of hydrocarbons, liquid methane, ethane, or more complex carbon compounds, rather than water. Life on carbon planets, if it evolved, would necessarily use chemistry adapted to carbon-rich, oxygen-poor conditions, potentially resembling the hydrocarbon-based biochemistry speculated for Titan. Lava worlds orbit so close to their stars that surface temperatures exceed the melting points of rock. These planets have surfaces of molten lava with atmospheres of vaporized rock, silicate gases that condense into mineral clouds and rain molten droplets. No life as we imagine it could survive on these surfaces, but some scientists speculate about exotic life existing in the upper atmosphere, where temperatures are lower, or about subsurface oceans trapped beneath the molten surface, where water remains liquid despite the hellish conditions above. Ice worlds covered by thick shells of water ice might be habitable not on their surfaces, which are frozen solid, but in subsurface oceans kept liquid by tidal heating from their parent planet's gravity. Jupiter's moon, Europa, and Saturn's moon, Enceladus, represent examples in our own solar system. Such worlds might be common around giant planets throughout the galaxy. The ice shell provides protection from radiation and impact, while the liquid ocean beneath could harbour extensive ecosystems based on chemical energy from hydrothermal vents rather than sunlight. These worlds would have dark biospheres, no photosynthesis, no dependence on their star, just chemosynthetic life, thriving in hidden seas. Rogue planets drifting through interstellar space with no star at all might still be habitable if they're massive enough to retain thick atmospheres that provide greenhouse warming through atmospheric pressure alone. A rogue Earth-mass planet with a very thick hydrogen atmosphere might maintain liquid water on its surface, despite receiving no starlight, heated only by residual internal radioactive decay and gravitational contraction. Life on such a world would exist in perpetual darkness, depending entirely on chemical energy and internal heat, completely independent of any star. A truly alien biosphere that could drift for billions of years through the void between stars. Binary planet systems where two similarly sized worlds orbit their common center of mass, like Pluto and Charon but potentially both habitable, might create unique conditions. Tidal forces between the planets would generate internal heating. The planets would raise tides on each other. If both have atmospheres, atmospheric circulation might be affected by the nearby companion. Life might evolve on both worlds simultaneously, potentially following different evolutionary paths, or life might spread from one to the other via meteorite impacts that eject material-carrying microorganisms between the two worlds. Trojan planets sharing the same orbit around a star, positioned at stable Lagrange, 0.60 degrees ahead of or behind each other, might exist in some systems. These planets would orbit at the same distance from their star, but would see each other as bright points in the sky, visible like particularly bright stars. If both are habitable, civilizations might arise on both, potentially detecting each other's presence long before achieving space travel, since the neighboring world would be so prominent in their sky. The different types of habitable planets extend far beyond Earth analogues to encompass ocean worlds with global seas, desert planets with scarce water, tidally locked eyeball planets with habitable rings, massive super-Earths with strong gravity, aerial biospheres in thick atmospheres, subsurface oceans beneath ice shells, hydrocarbon-based chemistry on carbon planets, and rogue worlds wandering starless through the galaxy, each type presenting unique challenges and opportunities for life, each potentially harboring biospheres as rich and complex as Earth's, despite being profoundly different in their physical conditions, demonstrating that the cosmos might contain not just one type of living world, but a vast diversity of habitable environments where chemistry, energy, and time have combined to create the extraordinary phenomenon we call life, scattered across countless worlds in forms we're only beginning to imagine. The incredible density of neutron stars. Imagine taking the entire mass of our Sun, a sphere so large that over 1 million Earths could fit inside it, and compressing it down to the size of a city. Not a large metropolitan area, sprawling across thousands of square miles, but just the central core, perhaps 12 or 15 miles across. This is a neutron star, an object so dense that a single teaspoonful of its material would weigh about 1 billion tons on Earth. To put that in perspective, that single teaspoon would weigh more than all the cars, trucks and buildings in a major city combined. This density is so extreme that it represents a fundamentally different state of matter, one that can only exist under the most extraordinary conditions in the universe. Neutron stars are born in the violent death throes of massive stars. When a star much larger than our Sun, typically at least 8 times more massive, exhausts the nuclear fuel in its core, it can no longer generate the heat and pressure needed to support itself against its own gravity. The core collapses catastrophically in less than a second, falling inward at speeds approaching 1/4 of the speed of light. The outer layers of the star, rebounding from this collapse, are blown away in a supernova explosion that briefly outshines an entire galaxy. What remains at the center, crushed under its own gravity, to densities that boggle the mind is a neutron star. To understand how neutron stars achieve such incredible density, you need to understand what happens to matter under extreme compression. In normal matter, atoms are mostly empty space. The nucleus of an atom containing protons and neutrons occupies only a tiny fraction of the atom's volume. The rest is empty space with a few electrons orbiting at relatively vast distances. In a solid object, like a piece of iron or a rock, the atoms are packed as closely together as the electromagnetic forces between them allow. But there's still enormous amounts of empty space within each atom. As you compress matter to higher and higher densities, you eventually overcome the forces that keep atoms intact. The electrons are stripped away from their nuclei, creating a plasma of free electrons and atomic nuclei. Compress further, and the electrons themselves are forced to occupy higher and higher energy states due to quantum mechanical principles. Eventually, at densities found in white dwarf stars, electron degeneracy pressure provides the support against gravity. The electrons can't be compressed any further without violating the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. But if you compress matter beyond even this point, as happens in the core collapse of a massive star, something remarkable occurs. The electrons are forced so close to the protons in atomic nuclei that they combine through a process called electron capture. A proton and an electron merge to form a neutron, releasing a neutrino in the process. This happens not just occasionally, but to nearly every proton in the collapsing core. Within a fraction of a second, the matter that was once composed of atoms, with protons, neutrons, and electrons maintaining their separate identities, transforms into a sea of neutrons, packed together so tightly that they're essentially touching. The neutrons themselves now provide the pressure that supports the star against further collapse. Just like electrons, neutrons obey the Pauli exclusion principle and cannot be compressed indefinitely. This neutron degeneracy pressure halts the collapse, but only after the matter has been compressed to densities comparable to that of an atomic nucleus. In fact, you can think of a neutron star as essentially a single gigantic atomic nucleus, several kilometers across, containing more neutrons than there are atoms in all the planets of our solar system combined. The density at the center of a neutron star is estimated to be around 500 million to perhaps a billion tons per cubic centimeter. At these densities, a cubic centimeter, about the size of a sugar cube, would contain more mass than Mount Everest. The entire mass of humanity, every person on Earth, could be compressed into a volume smaller than a grain of sand at neutron star densities. These numbers are so far beyond everyday experience that they almost lose meaning, but they represent real physical conditions that exist in these objects. The structure of a neutron star is complex and layered. At the surface, there's a thin atmosphere only a few centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, where matter exists in a crystalline lattice. Here, atomic nuclei, now incredibly neutron-rich and unlike any nuclei found on Earth, are arranged in a solid structure with a sea of electrons moving between them. This crust is extraordinarily rigid. It's been calculated that the material of a neutron star's crust is about 10 billion times stronger than steel. Deeper into the neutron star, at densities about 1 million times that of normal atomic nuclei, the inner crust begins. Here, neutrons start to leak out of the nuclei and form a superfluid that exists between and around the nuclei. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever. This neutron superfluid can exhibit bizarre quantum mechanical behavior on a macroscopic scale. Below the crust lies the outer core, where the density becomes so high that nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain charge neutrality. The neutrons in this region form a superfluid, while the protons form a superconductor, a state where electrical current can flow without resistance. These quantum fluids make up the bulk of the neutron star's interior. At the very center, in the inner core, conditions become so extreme that we're not entirely certain what happens. The density may exceed that of atomic nuclei by a factor of several times. At these densities, neutrons themselves might break down into their constituent quarks, creating what's called a quark-gluon plasma, or strange quark matter. Alternatively, other exotic particles predicted by physics but never observed might appear. The center of a neutron star is one of the few places in the universe where matter exists in states that can't be recreated or studied in laboratories on Earth. The incredible density of neutron stars creates gravitational fields so strong that they noticeably warp space-time. At the surface of a neutron star, gravity is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star's surface, though you would instantly be crushed and vaporized, you would weigh 200 billion times more than you do on Earth. A fall from even a tiny height of 1 centimeter would be fatal, as you would hit the surface at a significant fraction of the speed of light. This intense gravity affects light itself. Photons climbing out of a neutron star's gravitational well lose energy through gravitational redshift. Light that starts as high-energy X-rays at the surface might emerge as lower-energy radiation by the time it escapes into space. The gravity also bends light rays, causing light from the far side of the neutron star to curve around and become visible to an observer. This means you could potentially see more than half of the neutron star's surface at once, as light from behind the star bends around it to reach your eyes. The intense gravity also means that space and time are severely warped near a neutron star. Clocks at the surface of a neutron star run about 30% slower than clocks far away in flat space-time. This time dilation is a real physical effect. Processes genuinely occur more slowly in the strong gravitational field at the surface compared to regions far from the star. The rotation of neutron stars adds another layer of extremes to their already extreme nature. Many neutron stars spin rapidly, some completing hundreds of rotations per second. This happens because of conservation of angular momentum. When the core of the parent star collapses, any rotation it had is amplified enormously as the radius shrinks. Just as a figure skater spins faster when pulling their arms in, a collapsing stellar core spins faster as it shrinks. The result can be a neutron star spinning so fast that its equator is moving at a significant fraction of the speed of light. The fastest spinning neutron star known rotates 716 times per second. Imagine an object with more mass than the Sun, compressed to the size of a city, spinning around more than 700 times every second. The surface at the equator of this neutron star is moving at about 24% of the speed of light. At these rotation rates, centrifugal forces become significant, causing the neutron star to bulge at the equator and flatten at the poles. Yet even with this rapid rotation and the outward force it creates, the neutron star holds together, a testament to the incredible strength of neutron degenerate matter and the overwhelming power of its gravity. The magnetic fields of neutron stars are among the strongest in the universe. The collapse that forms a neutron star compresses and amplifies any magnetic field present in the parent star's core. The result can be magnetic fields 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields even stronger, up to 1,000 times more intense still. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms stretched by these fields become elongated, many times longer than they are wide, fundamentally changing their properties. These magnetic fields, combined with rapid rotation, power some of the most energetic phenomena in the universe. Charged particles, accelerated along magnetic field lines, emit beams of radiation from the magnetic poles. If these beams sweep across Earth as the neutron star rotates, we detect regular pulses of radiation, which is why many neutron stars are called pulsars. The precision of these pulses rivals that of atomic clocks, with some pulsars maintaining their timing to within microseconds over years or decades. The density of neutron stars also means that they have very deep gravitational wells. The escape velocity from the surface of a typical neutron star is about 150,000 kilometers per second, roughly half the speed of light. This means that matter falling onto a neutron star from a companion star in a binary system releases tremendous amounts of energy. The infalling material accelerates to these extreme velocities and slams into the surface with incredible force, heating to temperatures of hundreds of millions of degrees and emitting intense X-rays and gamma rays. Neutron stars can also collide with each other in binary systems where two neutron stars spiral together due to the emission of gravitational waves. When they finally merge, the collision creates conditions even more extreme than those in individual neutron stars. The merger produces a burst of gravitational waves that ripple through space-time, along with electromagnetic radiation across the spectrum. These collisions are thought to be the primary source of heavy elements like gold and platinum in the universe, forged in the incredibly dense, hot material ejected during the merger. The study of neutron stars provides a unique laboratory for physics under extreme conditions. The densities, magnetic fields, rotation rates, and gravitational fields found in and around neutron stars simply don't exist anywhere else that we can observe. By studying these objects, physicists can test theories about how matter behaves at nuclear densities, how gravity warps spacetime in strong field regimes, and how quantum mechanics manifests on macroscopic scales. Every observation of a neutron star, every measurement of its mass, radius, rotation, or cooling rate provides constraints on fundamental physics that cannot be obtained any other way, offering glimpses into realms of matter and energy that push the very boundaries of our understanding. The powerful magnetic fields of dead stars. When a massive star exhausts its nuclear fuel and explodes as a supernova, the collapsing core is compressed into an object of almost incomprehensible density. A neutron star, containing more mass than the Sun, packed into a sphere only about 20 kilometers across. This violent compression doesn't just create extreme density, it also amplifies the star's magnetic field to strengths that dwarf anything found elsewhere in nature. The magnetic fields of neutron stars are among the strongest in the universe, billions or even trillions of times more powerful than Earth's magnetic field, strong enough to distort atoms, affect the fabric of empty space itself, and dominate the physics of everything near these stellar remnants. To understand how neutron stars develop such powerful magnetic fields, we need to consider what happens during the collapse. Before the supernova, the massive star had a magnetic field similar in strength to the Sun's, a few Gauss at the surface, comparable to a modest laboratory magnet. The star's magnetic field was generated by convection and rotation in its interior, creating currents of electrically conducting plasma that produced magnetism through the same basic dynamo process that generates Earth's magnetic field. When the star's core collapses, it shrinks from a radius of thousands of kilometers down to only about 10 or 12 kilometers, a compression factor of more than 1,000. As the core collapses, magnetic field lines are squeezed together. The strength of a magnetic field is proportional to the density of field lines passing through a given area, so compressing the core concentrates the field lines, amplifying the magnetic field strength enormously. The exact amplification depends on the details of the collapse, but conservation of magnetic flux, a fundamental principle stating that magnetic field lines cannot be created or destroyed, only moved around, requires that the field strength increase roughly in proportion to the decrease in the star's cross-sectional area. Shrinking the radius by a factor of 1,000 increases the magnetic field by about 1,000,000 times. A star with an initial field of 1 Gauss would emerge from collapse as a neutron star with a field of roughly 1,000,000 Gauss, or 1,000 Tesla. This is just the starting point. Most neutron stars have magnetic fields measured in hundreds of millions to trillions of Gauss. Earth's magnetic field, for comparison, measures about half a Gauss at the surface. The strongest continuous magnetic fields produced in laboratories reach around 45 Tesla, or about 500,000 Gauss, requiring enormous electromagnets and tremendous amounts of power. Yet neutron stars casually exceed these laboratory records by factors of millions or billions through nothing more than gravitational compression. Rotation adds another layer of complexity. The collapsing core spins faster as it shrinks, just as a figure skater spins faster when pulling their arms inward. Another consequence of conservation of angular momentum. A star that initially rotated once every few weeks might emerge from collapse rotating several times per second, or even hundreds of times per second. This rapid rotation, combined with the intense magnetic field, creates the phenomenon we observe as pulsars. A pulsar is a rotating neutron star whose magnetic axis is tilted relative to its rotation axis, similar to how Earth's magnetic poles don't align perfectly with the geographic poles. Charged particles near the neutron star's surface are accelerated along the magnetic field lines toward the magnetic poles, where they emit beams of radio waves, X-rays, and sometimes even gamma rays. As the neutron star rotates, these beams sweep through space like lighthouse beams. When one of the beams happens to point toward Earth, we detect a pulse of radiation. The pulses arrive with extraordinary regularity. Some pulsars keep time more accurately than the best atomic clocks over short timescales. The Crab pulsar, formed in the supernova observed in the year 1054, rotates 30 times per second and has a magnetic field estimated at around 1 trillion Gauss. This field is strong enough to do remarkable things. If you could somehow place a human body in such a field, ignoring for the moment all the other ways a neutron star would kill you, the magnetic field would be strong enough to distort your atoms. The field would force electrons into different orbital configurations, changing the chemical properties of matter and making normal biological chemistry impossible. But some neutron stars have magnetic fields even more powerful than typical pulsars. These objects, called magnetars, possess the strongest magnetic fields known in the universe, reaching 10 to the 15th Gauss, or 1,000,000,000 Tesla. These fields are so strong that they affect empty space itself. According to quantum electrodynamics, the quantum field theory describing how light and matter interact, extremely strong magnetic fields can cause the vacuum to behave in strange ways. The vacuum can become birefringent, splitting light into two beams with different polarizations, similar to how certain crystals split light. Virtual particle pairs, electrons and positrons that normally pop briefly into existence and then annihilate, can be affected by the field, altering how light propagates through the vacuum. In magnetar fields, atoms are stretched into elongated shapes, becoming needle-like structures rather than the familiar spherical electron clouds. The magnetic field overwhelms the electric forces that normally determine atomic structure, forcing electrons into highly unusual quantum states. Matter at the surface of a magnetar exists in forms never encountered anywhere else, with properties unlike any material found on Earth or in laboratory experiments. Magnetars reveal their presence through sudden outbursts of X-rays and gamma rays. The magnetic field stores enormous amounts of energy. In the strongest magnetars, the magnetic energy exceeds the binding energy holding the neutron star together, creating immense internal stresses. The neutron star's crust composed of crystallized nuclear matter, occasionally cracks under these stresses in events called starquakes. When the crust suddenly shifts, the magnetic field lines snap and reconnect violently, releasing tremendous bursts of energy in seconds or less. The most powerful magnetar flare ever observed occurred in December 2004 from a magnetar designated SGR 1806-20, located about 50,000 light-years from Earth. In 1/10 of a second, this flare released more energy than the Sun emits in 150,000 years. The radiation from this event saturated detectors on satellites throughout the solar system and measurably affected Earth's ionosphere, despite the enormous distance. If this magnetar had been located only 10 light-years from Earth instead of 50,000 light-years away, the flare would have caused a mass extinction, stripping away the ozone layer and exposing the surface to lethal radiation. The origin of magnetar fields remains somewhat mysterious. The simple compression of the collapsing star's field cannot account for fields this strong. Magnetar fields are hundreds to thousands of times stronger than what compression alone would produce. Several theories attempt to explain the enhancement. One possibility involves a dynamo mechanism operating in the first few seconds after the neutron star forms, when the core is still extremely hot and turbulent. Convection in the proto-neutron star, combined with rapid rotation, might amplify the magnetic field through a dynamo process, similar to how Earth generates its field, but operating under extreme conditions for a brief time. Another possibility involves the formation mechanism itself. If the collapsing core rotates very rapidly, near the maximum possible rate, differential rotation between the inner and outer parts of the core might stretch and amplify magnetic field lines, winding them up like a spring and creating the immensely powerful fields observed in magnetars. This would suggest that magnetars are born from progenitor stars that were rotating particularly rapidly before collapse, or from binary star systems where mass transfer spun up the star before the supernova. The magnetic fields of neutron stars gradually decay over time. The field energy is dissipated through various processes, including emission of electromagnetic radiation and heating of the neutron star's interior. Typical pulsars with fields around 1 trillion Gauss might maintain those field strengths for millions of years. Magnetar fields, being much stronger, decay more quickly, possibly over tens of thousands of years. As magnetars age and their fields weaken, they might become ordinary pulsars indistinguishable from neutron stars that never had magnetar strength fields. This decay helps explain why magnetars are relatively rare. Astronomers have identified only about 30 confirmed magnetars in our galaxy, compared to thousands of ordinary pulsars. If magnetar fields decay on timescales of 10,000 to 100,000 years, and they form perhaps once every few hundred years in our galaxy, then at any given time, only a few dozen active magnetars would exist, which matches observations well. The magnetic fields don't just affect the neutron star itself, they extend outward into space, creating a magnetosphere. Charged particles near the neutron star cannot cross magnetic field lines easily, so they become trapped, spiraling along the field lines. The field forces these particles to co-rotate with the neutron star out to a distance called the light cylinder, where the co-rotation velocity would equal the speed of light if the field could enforce it. Beyond the light cylinder, particles can escape along the field lines, carrying energy and angular momentum away from the neutron star. This energy loss causes pulsars to gradually slow down. The Crab pulsar's rotation period increases by about 38 nanoseconds per day, as it loses rotational energy to the magnetic field and the wind of particles it drives. The rate of slowdown reveals how much energy the pulsar is radiating. Young pulsars with strong magnetic fields slow down quickly. Old pulsars with weaker fields slow down more gradually. By measuring both the rotation period and the slowdown rate, astronomers can estimate a pulsar's age and magnetic field strength. Some of the fastest spinning pulsars, called millisecond pulsars because they rotate hundreds of times per second, have much weaker magnetic fields than typical pulsars. These objects were spun up to high speeds by accreting matter from a companion star in a binary system. The infalling matter transferred angular momentum to the neutron star, spinning it up, while simultaneously burying the magnetic field under a layer of accreted material, weakening the external field. These recycled pulsars have been rejuvenated by mass transfer, given a second life as rapidly spinning objects with relatively weak fields. The study of neutron star magnetic fields connects to fundamental physics in several ways. These fields exist at strengths where quantum electrodynamics predicts effects that cannot be tested in any laboratory. Observations of magnetars and the radiation they emit provide the only way to study matter and vacuum behavior in such extreme magnetic environments. The fields also affect how nuclear matter behaves at the neutron star surface and in the crust, influencing the equation of state, the relationship between pressure and density of matter at nuclear densities and beyond. Binary systems containing two neutron stars allow even more exotic magnetic interactions. When two magnetized neutron stars orbit close together, their magnetic fields can interact, possibly reconnecting and releasing energy. As the neutron stars spiral together, driven by gravitational wave emission, the magnetic fields might play a role in the final moments before merger, potentially affecting the gravitational wave signal and the electromagnetic radiation emitted during the kilonova that follows. The powerful magnetic fields of dead stars represent nature operating at extremes impossible to recreate artificially, fields where quantum effects modify the behavior of empty space, where atoms are distorted beyond recognition, and where enough energy is stored to power the sun for millennia, all concentrated in objects small enough to fit inside a city, yet massive enough to contain more matter than an entire star. Fields that define the physics of these remarkable objects and make them among the most extreme environments existing anywhere in the cosmos.